Nipun Batra is an associate professor in computer science at IIT Gandhinagar. He previously completed his postdoc in University of Virginia. He completed his PhD from IIIT Delhi, where he was TCS PhD fellow, and his group called Sustainability Lab broadly works in machine learning, sensing, and computational sustainability. Problems like smart building, air quality, wearable healthcare. His work has awarded including ACM 6 Energy Rising Star Award, Young Alumni Award from IIIT Delhi, the best PhD presentation at ACM Genesis, and best demo at ACM Genesis, and the best video coming at ACM Editor. Thank you.
Thank you for the introduction. So there's a funny thing about awards. You're typically given awards like Young Alumni Award when you're not young, when you're no longer young. You're given awards like Rising Star Award when you yourself have rising stars with your team and under your team. You're no longer rising, like you have rising stars. So with that, I wanted to today discuss about exploring health and wellness through respiratory sensing. So in the previous talk, we did have a talk about bats, COVID, respiratory sensing. I hope you can see the loop. It was not planned that way. It just turned out naturally. So this is work we have done with Rishiraj and Ayush, who are PhD students here. Rishiraj is a graduated PhD student and Professor Mayank at CMU. So we unfortunately do not know that there is a significant burden of chronic respiratory diseases. These include various things like COPD, asthma, bronchitis. Amongst COVID was one of them which really shook the whole world. You can see that the regions in dark red is where we live. So the respiratory diseases are very significant in the Indian subcontinent. And we will be using a terminology, a very common terminology as a starting point, which is the respiration rate. So it's something which we take for granted that we are breathing in and out. We will say that respiration rate is the number of breaths you're taking per minute. And it turns out to be an important biomarker to diagnose respiratory illness. So question to all of you before I go ahead. What do you think happens when you experience fever? What happened to you when you had COVID fever? What were the kind of symptoms that you had? Forgotten? No one wants to remember that phase? Sorry? Breathing irregularity, okay. People had to wheeze, people had a hard time breathing, they had to put more effort to breathe, that was one. The other was that your pulse rate got more, your temperature was more. So typically when we go to doctors, we may think that it's mainly the temperature which we need to get diagnosed. So during COVID also, if you remembered, people had those thermal sensors at the airports, at the entrances to malls, etc. So they would only look at that. Sometimes sensors such as thermal sensors can be inaccurate, especially if they're not calibrated well. Secondly, sometimes the temperature shows a bit of a lag. You may be experiencing symptoms of fever, but there may be a bit of a lag in showing the temperature increase in your body. Whereas certain other biomarkers, including respiration rate, can shift more early. So think of this as someone with COVID, they came to the entrance of an institute, they were screened thermally, and they did not show any raise in temperature, but they had an increase in the respiration rate. They were showing some symptoms, but these were not the ones you were monitoring. So there are these different conditions which have an associated biomarker in terms of the respiration rate, like stress, pneumonia, COVID-19. COVID-19, as some of you had pointed out, is more about irregular breathing, whereas pneumonia and cardiopulmonary arrest are about 20-30 breaths per minute. Before I go ahead, what do you think is the number of breaths you take per minute? On average, what would you expect that number to be? 100, 72, 85, what is that number? 15, okay. Any other guesses? 80, 20, okay. 12. No, you shouldn't be answering. You have written papers on this. Someone else should be answering. What is the number 72 that we hear a lot? 60 to 80. So heart rate is not the same as respiration rate. I hope everyone understands this. So there are these different biomarkers. So in a typical person, the respiration rate is typically 12 to 20. What about kids? Do you think they breathe quicker or they breathe slower? Quicker. So they typically have much higher breathing. So therefore, what we're claiming is that unfortunately the respiration rate is hardly monitored. Like how many times do you remember going to a doctor and them actually monitoring your respiration rate? They will probably monitor your pulse, they will look at your temperature, but they are not very often looking at your respiration rate. And we're saying that the respiration rate is an important biomarker. Now, how many of you have used smartwatches? Apple smartwatch, Samsung, Xiaomi, any of those, or a smart ring? How many of you are using it? Okay, how many of you are happy with it? How many of you have a placebo effect that you are now active in your life because you have a smartwatch which is showing you the number of steps that you've taken? Or how many of you took a smartwatch because you thought you'll become more active that way? Because you'll monitor and then but then you realize it does not really change anything. After 1 week, you're still the lazy couch, lazy potato couch and watching Netflix, right? So, coming back, so what are the things which the smartwatches give us or the smart rings give us? Anyone? What all do they tell you? The pulse, okay. What else? Oxygen saturation, okay. Sorry, footsteps, the number of steps that you have taken, okay, good. What else? Calorie count, okay. And I think the calorie count is probably one of the more like what you think is useful, because now you'll think that I have burnt enough calories so that now I can eat 2 scoops of the ice cream instead of 1, right? Of the butterscotch which was kept outside. What if I told you that you were being told a lie? That you are actually overeating the ice creams, the calorie count on your smartwatch is wrong. And we'll see that it's not wrong by 2%, 3%. It can be wrong by about 35 to 40% in leading smartwatch. So that's being shown in some study. Before I go to that, I want to briefly discuss 3 aspects which we'll discuss in today's talk. We'll be looking at the aspects of wellness, where we'll discuss the first system, JoulesEye, which is to measure your energy expenditure, which is a calorie count in simple words. Second, we will be looking at diagnosing which diseases such as sleep apnea. And the third one, we will be looking at measuring your lung function. So each of these work you will see is a combination of some commercial off-the-shelf sensors and some computer vision machine learning kind of techniques. Coming on to the first work, we will be using this terminology, energy expenditure, calorie consumption, all of them interchangeably. This is the amount of energy that you're expending using various activities. Now, how many of you have seen a system like this? Has anyone seen a system like this? Okay, where have you seen such a system? Sorry? Gym, okay. Yeah, you would see some athletes including high performance athletes typically use this kind of a setup. Sometimes they use in 2 purposes. One is to restrict to try and exercise in harder conditions. The second kind of setup is where they are actually putting this tight mask kind of a system where they are monitoring your inhalation, exhalation. So this is what will use to measure your energy expenditure or the calorie consumption. So throughout this talk, and I think this will be a recurring theme across multiple such talks, like even in Prashant's talk you saw that there is a gold standard way of measuring something which is probably too expensive, too inefficient, too manual, etc. Like for the parking cars, you could actually have one BTech student from the nearby college stand at each and every intersection and they will do a very good job. But is that scalable? Is that cheap? Is that manual, etc.? Similarly, we need to first figure out what is the gold standard, what is the correct best measurement I can get. And then when we build such systems, we need to see that what is the proxy that I can get to that. So here, this Machine looks at your oxygen consumption, your carbon dioxide, which is produced during respiration, and it's a very closed system. Importantly, closed system. So in the perfect sense, every molecule of O2 or CO2 which is being released or inhaled is just within the system. It's not going out in a perfect setting, which is not ideal, which does not happen. So here they're trying to measure energy consumption as a function of multiple such parameters. If you notice carefully, you can see that there is also this chest belt like setup, some belt on the chest. You can also see that we're trying to measure your heart rate, which is comparatively easier. We are also looking at the volume of the oxygen and the CO2 of the gases, the net difference of oxygen content between iota and vein, and some gamma factor, which is oxygen to energy coefficient. So let's think of this as some system which utilizes your heart rate, your oxygen gap, the difference between oxygen and CO2, etc. And then there's some black box algorithm, like which is black box to us, but it's proprietary to the machine, to the company which has created this, which will give you a calorie consumption. Now, smartwatches have been doing this the same way. So the question is that why don't we use smartwatches? Firstly, as all of you pointed out, smartwatches will give you the step count, which is fairly accurate, I would say fairly robust. How do you think they get the step rate? Do they look at the GPS trace? Then what could they use? Accelerometer, gyroscope, magnetometer, etc. So these are basic sensors you can be using. Heart rate, how do they get you the heart rate? Heart rate is the rate at which heart is pumping out blood. Whenever the blood is being pumped out, it reaches out to the extremities. That's the longest distance from the heart to the extremities. You have various extremities. You have the extremities of the hand and of the leg. The hand is much easier to instrument. You can't be wearing a smartwatch on your foot nails. It wouldn't be that cool to carry a 50,000 Apple Watch hidden beneath your shoes. So you want to be putting these at the peripheries where it's easy. That's why we have different sensors. That's why the SpO2 monitor is here and not somewhere else. So that's also an interesting problem. You can also use other peripheries like your earlobes. So you can then get the heart rate. Whenever the blood is pumped, it will cause a change in the blood configuration reaching here, and that would lead to some change in the optics. The amount of redness will change very minutely. I don't know if any of you have tried this or not. You could actually experiment. You could use your phone. You could open the camera app, keep your hand like this, and record a video. And you will perhaps, okay, sorry, I didn't create a video. If you have a very good vision, you will be able to see some light fluctuation, right? So that will give you the heart beating and reaching the extremities. So now you can use some very simple algorithms to get this kind of a waveform. So the smartwatches are getting the step count, they're good at getting the heart rate, and they also give you the energy expenditure. But important fact that smartwatches can sometimes estimating about 37% wrong, which is to again say that your gulab jamun and your butterscotch ice cream, you have to wait, you have to be very careful about that. Like, don't just rely on this, listen to other body signals also. This is as per this particular study published at JMIR. So what we want to see is that the smartwatches in this form, which is given by the domain experts, which is again another recurring theme that you will see in this talk and in various talks. You will see that there is a gold standard which is being prescribed by the domain experts, and then people are using it. Secondly, there are some gold standard physics equations or some equations well established in the domain, which those domain experts use. But generally, in some computational method, we will end up approximating some of them based on the sensing capabilities that we have. So we want to then see the smartwatches amongst these factors is probably only looking at your heart rate. Maybe your age, gender, etc. also it's looking at. But most probably amongst these, it cannot get the other parameters. It's only able to get your heart rate. From your heart rate, it's trying to establish your your energy expenditure, which may or may not always be correct. You can also think of extreme situations. You take a very healthy swimmer, you'll see that how their body will respond to different kind of physical stresses. Importantly, this was to show that it's not smartwatches are relying only on the heart rate. So we have these two ends of the spectrum. Another recurring theme that you will see a gold standard which exhibits certain properties, and then you will see some existing machines which are commercially off the shelf, which are very easily accessible. So calorimeters are very accurate. They monitor the O2 concentration, whereas smartwatches are only looking at your energy expenditure, but they're inaccurate. They do not monitor O2. They're mainly relying on heart rate to measure energy expenditure. So whenever you see such a spectrum, that is where academic researchers like, just researchers like us try to fit in. What can we do? Where do we optimize it so that we can get the best of both the worlds? That's where we propose a system called JoulesEye. Joules as in literally means joules, energy, and I means like a vision-like system. So we will be using some computer vision-like system to measure your energy expenditure. What we're saying is it's more accurate than the smartwatch. It is less accurate than the calorimeter, but it's not intrusive. So we don't want to be carrying that mask and going that full mask wherever we want to measure our calorie consumption. So imagine that I showed you the sports complex. Now, if I have to measure your energy consumption, your calorie burn, you run with that around the sports complex. It won't be that practical, feasible for non-specialists. So the idea behind this system is very simple. We will be using a smartphone attachment or a small smart watch like prototype. We are showing the smart watch like prototype here. If any of you have good industrial experience, bus, this is what current prototype will buy this. So I want to first show you and then show you how we would use this sensor. So this is the feed from a thermal camera. What do you observe around the nostrils? Okay, let's do one exercise. Keep your finger near your nostril and breathe slightly longer in and out. What do you observe? Yes. Yeah, there is a temperature differential between your exhalations and inhalations. So we are going to look at that to get a sense of your respiration when you're breathing in and breathing out. And I thought I'd also give a demo of this whole system in place. Let's see if this works. So the rule of demos is that they often do not work under live situations. Like I had a very good start to this by just breaking this handle of the sensor. Let's see if I am lucky to get this working or not. So what I'm showing is a thermal camera. There are other ones also, like Fleur makes those cameras. Those can be attached to your iPhone, Android phones via USB-C. I think I was right. The camera has, okay, this one is working. The USB one has, okay, started working. This is me, by the way. Just focus on my nostrils. So one, we got a sense of that this thing actually works, and it's not very difficult to do. I will also show doing the same thing through some Python code. In the demo which follows, you will see the underlying technology behind this. So I hope you got a sense of the waveform which is generated. It's not always perfect. The amplitude can shift a bit, but you still get a sense of, if you were just looking at it from a frequency spectrum, frequency analysis perspective, you should be able to see that there is a constant rate at which this person is breathing. So this shows you the first kind of problem we will be solving, which is to detect your nostrils, and from your nostrils, we should, if we just monitor that, we should be able to get your respiration rate. So we looked at this in a laboratory setup where we had the participants perform different kinds of activities. We made them run on a treadmill. We made them run on the ergometer, which is a bicycle. So we had them do some of these exercises. And the next obvious question which you might be thinking is, how do you detect the nostril? So here I showed you that this is my nostril, and then this is the waveform that I'm getting at my nostril. So how do you think the nostril detection works? Yes. Sorry? Location of the eye. So there are multiple methods which you could be using. One specific method which she's saying is like the landmark detection, which is what we are showing here. There are different algorithms which specifically map out the face via different landmarks, and then they're trying to map them out. And then there are very nice implementations of these. We observed that these work very well in the RGB domain, in the regular imagery that we get, but they do not work very well for the thermal imagery. Now, the other kind of algorithm is what Prashant spoke in the morning, which are like object detection kind of algorithms, which is what we can use, which we end up using. We also looked at certain variants, which we will discuss, perhaps skip, which is to keep the track over time. So one is given a static frame, given a single image, thermal image, I have to tell where my nostril is. Second, you have to do the tracking over time. Like if you're playing some sports, you have to track the ball over time. Given a single image, I can tell something. Given two images, I should have some smoothness between the ball between the different frames. So we ended up using some specific algorithms. I will not get into the details of that. In this case, it's called discriminative correlation filter. But later on, we have also looked at optical flow, dense optical flow. There are variants to it like sparse optical flow, dense optical flow, which also ended up working well. So we won't get into the details of that because we just use those as existing solutions ported to our problem. But importantly, here you can see that this person is exercising very vigorously, and the marker, which is noting down which is trying to locate the nostril, is still keeping a very good track. Now, once we have this tracking done, what do you think is the next step? Identifying when the Yeah. So after you have done the localization, all you need to figure out is that waveform which we got, which we can simply get by just looking at the average pixel intensity in this box. You could do something better. You could use segmentation to actually get the exact location of the nostrils. But then again, you will end up with different kinds of problems. Especially, this is a very simple example. If you were to look at it from far, etc., then you have the same problems which Prashant was mentioning in the morning. Small object detection in large images is typically a hard problem. You could do that. You could use different kind of transform. You could use segmentation algorithms. So what we now wanted to get is, we have now estimated the respiration rate. Now we eventually want to get the energy expenditure. That was the goal. So first we will estimate the exhale day from respiration rate, and then from that we will estimate your energy expenditure. At this point, it's mainly a machine learning problem. So initially it was firstly figuring out from the domain expertise talking to the domain experts that what is missing, what is the gold standard, what is missing in the current technology. Once we figured that out, we figured out a way to do signal processing and some signal capture to get the signal of interest, which is your respiration rate. After that, it's a machine learning regression problem, which regresses from your respiration rate as well as your heart rate as inputs to your energy expenditure, calorie count. Calorie count, we are essentially saying that we will end up learning something which is an equivalent of this formula, which works in practice similar to this formula without explicitly knowing this formula. So an important aspect of all such studies is the user study and the design. So we did this study with about 54 participants where we had two kinds of activities. Cycling on the ergometer. Ergometer is a fixed cycle. 41 participants and 13 participants running on a treadmill. We had about 24 females and 13 males. And the age was somewhere between 25 to 54. So what we observed is similar to the prior literature, that the error that we get using smart watches was around 37.6% in the mean absolute percentage error in terms of the energy expenditure across the different sessions. And when we got our respiration rate and fed it into our machine learning model to get the consumption, the mean absolute percentage error compared to the gold standard is about 6%. So there's a significant reduction in error compared to the existing variables. Importantly, what we also observed is that, so we'd expect that the people who have a high BMI are the ones perhaps who want to very seriously track their energy consumption, their calorie consumption. So the smartwatches overall give 37% error, but on people who are overweight, the error is 52%. Right? So it's defeating the purpose. Whereas for us, we can see that the errors are comparable, not too significantly bad for overweight people, which we believe is an important thing to highlight, that the intended population is can be athletes, can be overweight people also, but we want to ensure that across the different groups, the error does not follow any specific pattern. Yes. 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 Okay. So, so this is an excellent question. So smart watches like Apple Watch and perhaps Galaxy Watch, etc., they want to create a user profile, and based on the profile, they want to answer the question as in how much calorie consumption that you have. So we, before the study, we ensured that each participant's details were entered correctly. So we did that. But this is an important aspect. Sometimes people ignore this and the results can be very off. So it's important in research that we do not purposefully try to beat down the state of the art. I have sometimes unfortunately seen students do that. They will not run the state of the art algorithms in the best possible configuration. They want to just beat the previous algorithm. Do whatever. I am better than the previous state of the art, but they will not run it properly. Their algorithm, they will give it all the love in the world. They will run it for all the possible hyperparameters. The state of the art algorithm just run for one specific seed, it didn't work well. Okay, so we are better than state of the art. We have to be careful about that. And another important thing, that the camera which I showed you, this particular camera, yes. Yeah. So the study design is slightly non-trivial here, because once you wear the gold standard, you cannot actually, like, our nostril is not visible. So you have to do it in two phases. I will defer the details to the paper. I can share that. But the important thing is that you have to carefully design it in a way that the intervention is applied correctly. But it's a very important question on how to figure out a study design. You cannot, so there are systems in which you can measure your particular quantity of interest and the ground truth in parallel. In this case, we could not do that. We have to do that serially. We have to do it sequentially. So another important question, that the sensor which I showed you seem to give you a very high quality image. But very often you don't want to be using such expensive sensors. This is probably a 20,000 rupee sensor. You maybe want to use cheaper sensors as you want to scale. So what we studied was, can we use a 24 pixel thermal camera? The feed is significantly poorer, but even with a 24 pixel camera, if we use heart rate information as well, we can get the error down to about 10%. So this is again trying to show the point that oftentimes we have to do a compromise between multiple modalities and the resolution across them. But importantly, we can bring it down to fairly good accuracy with one additional modality being the heart rate. 24 pixel is significantly lower compared to 256 pixel. So this is the prototype which we have created. You can notice that that was the smartwatch like prototype, and this is the quality of the signal that you're getting. So this is the feed that you're getting from it, because it's only 24 pixel. Right? So try to map out my entire upper body using only 24 pixels. You will likely get a very poor signal, but even from that poor signal, the respiration, you can see that the blobs light up and they become darker. So you can, through that, also get this respiration rate, as you can see here. So to summarize this first piece of work, we have looked at respiration rate combined with heart rate, and we are able to get very accurate energy expenditure or the calorie consumption done on a study of about 54 people. The conventional trackers are not currently able to use your respiration rate. We believe that going forward, if they use the respiration rate, their accuracy will only improve. So with this, I'll end the first part of the 3 parts that I have. I can pause for a minute and take questions before I go to the next part.
So the energy consumption was a function of multiple parameters, right? So did you do an ablation study, or was these 2 parameters, respiration rate and the heart rate, based in performing the calculation? Was that so?
Okay, so it's a very good question. Let me come back to the equation which I showed. So in this equation, we are not able to access most of the parameters. They are internally available to this indirect calorimeter. We don't have access to those. And we do not also have access to the specific equation that they are using. So therefore, we cannot use them and then figure out the feature importance. Instead, we end up creating a different algorithm which is working on the available features which we have. And we overall compared that our accuracies are similar, like not too far off.
Okay. So when you compare it with the gold standard, so they don't tell you the equation, or like?
So the gold standard would do it in a proprietary fashion. We do not know which specific equation which they would use, etc. What is the and what is the population factor that they've taken. So for instance, maybe for certain races, this gamma factor would be different. For another race, it might be different. So we typically see this in some medical devices. Other questions? Okay. So next, I'll go on to the second part of the talk, which is on diagnosis, and I will be looking at apnea I, which is to measure sleep, a condition known as sleep apnea. Oh, sorry, I'm also taking the liberty to sit. I have a bit of an injury on my leg, so I hope that is okay with you. So, how many of you have roommates who snore, or people in the family who snore? How many times does that disturb you? Do you also just get angry and snore back even louder to try and get your revenge? Right? So very often we think that snoring is a good sign, right? We think snoring is a good sign that the person is very tired and now they're getting a good night. But unfortunately, that snoring could sometimes also be sleep apnea. So it's a very common condition. So this specific condition is a disorder where people are unable to breathe or they have shallow breaths during the sleep. And then in the middle of the night, they will just wake up with a gasp where they're out of breath. And they will perhaps wake up next morning and they will not have had a sufficient night's sleep. They will obviously be very tired. So This is how we typically breathe normally. We can see that the airflow goes from the nostril to the windpipe, but you can also see that there is tongue here. Right? So we take it through the nostril and then. So typically we never think that the tongue will do anything. The tongue supposedly does not have anything to do with respiration, but when this particular condition known as obstructive sleep apnea occurs, you can see that the tongue is blocking the back of the throat, and then you can see that there is this choked passage, right? Now, whenever there is a choked pipe or a choked passage, do you see that it will give you a flute-like sound? Like not that pleasant flute-like sound, but that's where the sound of the snoring comes in. You can actually see those vibrations if you look at a very micro level. So that is what is leading to like snoring could be because of sleep apnea. Because if it's due to obstruction, then this is what you will observe. Now the tongue will fall and the windpipe will get blocked. Because of that, there will not be enough airflow, and because of that, eventually people will have a mini panic attack, and then they'll wake up, and then the condition will normalize. Now, this is the big number we have to be very, very careful about. 1 billion people suffer from apnea, sleep apnea. What is the total population of the world? 8 billion, 7 billion, something like that. So 1 in 8, 1 in 7 we have about 50 people in the room. Right? So if we just go by the simple statistics, it should be 7 or 8. I hope not, and because it's also a younger cohort, I'll also count us as young for now. We will, but you can unfortunately see that again in the subcontinent that the rates are very significant. The number of people who are suffering from apnea is a very large number. And another important thing, in the vast majority of these cases, the patients are not diagnosed or they're not diagnosed early enough. So beyond just the sleep apnea, they also have a risk of co-occurrence of other diseases such as cardiovascular, metabolic dysfunction, impaired brain function, even depression. So you typically see that if the sleep is not well, it will unfortunately lead to other disorders also. If you fix sleep, the other things may also go away. So again, we come to the old pattern. How do we measure sleep apnea? We previously, for calorie consumption, we looked at the gold standard, which was an indirect calorimeter. For sleep apnea, we have to go to a specialized clinic called a sleep lab. So this is a photo from a sleep lab at AIIMS, New Delhi, where this person is being monitored overnight. So imagine you have to sleep overnight in this for 8 hours or so, and your condition is being monitored. Will you get even a minute's sleep in this? Unfortunately, that's the case, that the monitoring of sleep apnea does involve so many things. So it's incredibly hard to even get diagnosed. So that's one thing, that this particular test is called polysomnography. And you can also actually try and break this thing down. Poly, multiple. Somnography, somnos related to sleep. Graphy means like you're trying to measure different parameters and trying to use them to get some clinical correlation. You have multitudes of sensors. Other important thing, because this test setup is highly specialized, sometimes there can be waiting periods of about a year to get an appointment. Right? So imagine the plight of people who have to get this diagnosed, have to wait for a year. Sometimes they have to come from all across the country because these labs are not present everywhere. Like while we have them in AIIMS Delhi, they are perhaps not available in majority of the hospitals. So this is the state of the art. This is the current status quo. This is how sleep apnea is currently diagnosed at sleep labs using polysomnography. There are other methods also. So they end up measuring different kinds of signals, including your brain activity, including your eye movement, including your airflow closer to your mouth and your nostril, your muscle tone, the muscle activity, your cardiac activity, your thoracic muscle, which is around this point, your abdominal muscle, your oxygen saturation, your leg movement, etc. So eventually they will end up creating these kinds of time series graphs, which is looking fairly complicated. A question for you so that your brain also remains active. Why do we require brain activity? Why do you think we require brain activity in this while trying to diagnose sleep apnea? Yes, excellent. So by monitoring brain activity through the EEG, you're trying to monitor the different sleep stages, deep sleep, etc., or REM sleep. What about eye movement? Why do we need eye movement? REM sleep, rapid eye movement. So it's a sleep stage where the eyes will very rapidly fluctuate. Nose and mouth airflow. Why do we need that? Respiration, right? So essentially respiration. Muscle tone, cardiac activity. Sometimes they are used as proxy of activities. Like in the middle of the night, if you wake up, that time period should not be used. So you could use that. Thoracic muscle, abdominal muscle. Why do we need that? Yeah, right. So why don't all of you just close your eyes for 30 seconds? This is not a breathing session, but let's do this anyway. Close your eyes for 30 seconds. Breathe in and out and tell me what all changes in the body. Okay, when you inhale, the air goes from your nostril to your lungs, and what expands? Do you see some expansion in your chest and your stomach, right? And when you breathe out, you again contract your abdomen and your chest. You blow the air all the way out from your nostril out, right? So therefore, your breathing in is going to be impacted. You can measure your breathing in at your nostril as well as in your abdomen or your thoracic muscle. Similarly, the breathing out also. So therefore, there are two different places, two different spatial locations where you can monitor breathing. And we need both of them. We'll see why. Oxygen saturation, leg movement, again, they are considered important for different other reasons. So this is the kind of waveforms that you will get. This is what the doctors will see. They will have specialized doctors look at these reports and then annotate whether, so you can see there is snore event, PTAF, airflow, etc. And then do the annotations to figure out if there are any abnormalities. So what we're saying is that we have to again follow the domain expertise. Previously, we had some domain expertise in terms of how the calorie consumption happens. Now the domain expertise comes in the form of the sleep medicine guidelines by the American Association. So they say that we can diagnose sleep apnea while looking at the nostril as well as your thorax abdominal segment. So we end up creating this high level overview of this system called Apnea, where we'll use a thermal camera, which you previously saw in JoulesEye, similar to that. We will have some signal extraction to get different components, maybe get your nostril as well as get your chest respiration, thorax respiration. And after that, at the end of the night, you want to get a classification report, how many different kinds of apnea events that you had. I'll get into the definitions of these, and then the diagnosis is done by the doctor. So again, this is a kind of a tool where this entire report is now sent to the doctor. So this is not really a prescriptive tool. This is more of a diagnosis tool where the doctor is in the loop. That is very important to say that this is not going to replace the doctor. This is just making their work easier, and this is also going to make it much more convenient for the patients. We'll see why. So this is our setup. Let me show you the previous setup. This is the status quo. This is our setup. Can you see that this seems significantly easier, significantly lesser burden on the participant? They can move around, they can do whatever they want. There is a single thermal camera placed near the bed at an appropriate angle, and then they view it. Why thermal? Why not RGB? Okay, one. RGB may or may not be able to get your respiration through the nostril. RGB, interestingly, will still be able to get your respiration via the chest. How? The movement of the chest and the thorax, that you can still get. Why? Any other reason why you might prefer a thermal over RGB? Okay. Okay, when the nostril is not visible, you still want to have some signature. Yeah, privacy. So RGB will be very like will reveal a lot of details about you, whereas thermal will be much better from a privacy perspective. So this is the video frame which we get from a thermal camera. You can again notice a similar thing. In the nostril, you can see them light up and light and become darker. And this is the actual signal that we are getting once we have identified this region of interest. The interesting thing about thermal imagery is that they work, as he was mentioning, they work not only when you're in the supine position. So there are typically 4 positions in which you sleep. So let's again do a COVID check, COVID questionnaire. In COVID times, what was the sleeping position that was typically recommended when people went out of breath? Does anyone remember? Stomach down, which is typically known as the prone position. That is the prone position. This middle one is known as a supine position. You are like you're sleeping on your back, and then you have a left and a right position. So in the supine position, you can very clearly see the respiration. Interestingly, in the left and the right position also, you can see the respiration. Again, this might be much more harder with different modalities, but here you can see. So the respiration through the nostril is perhaps easy. Like we can actually see a temperature differential. What about the thorax abdomen? How do you think we can sense that? So when you breathe in and out, your thorax region will move up and down. How do you measure that using a thermal camera? Okay, okay. Yeah, so I think you're on the right track. So essentially what we want to do here is to firstly use this domain knowledge. So the clothes which are in touch with you will typically be warmer. The part of the cloth which is in touch with me will typically be warmer. The part of the cloth which is not in touch with me will be slightly cooler. So this is typically, you will observe this, that your human body and anything which touches it is warmer than the surroundings. This is assuming that you are not artificially creating a situation where you are giving some excruciating pain to an individual just to prove me wrong. But in most cases, you will see this kind of a situation. So what we end up wanting to do is to identify a few points which are at the interface of the outside world and your body. So if we can do that, then we'll see that these points have 2 regions. One is a hot region and the other is a cold region. Now, once you figured these points, you can then track them over time. So if you were to do the tracking of these points over time, you will again get the movements. So this I'm showing through one particular algorithm, which is by finding out the gradients and doing some thresholding. The gradient is where there is a maximum change. So if we employ filters to get the gradients from this, we will perhaps get these points where there is a maximum temperature change in a short region, in a small region, spatial region. And if we track those pixels, those small regions over time, we will get, after some post-processing, we will get this pixel intensity. That's one way. The second is, as we discussed earlier, we could again use optical flow. So the details I'll skip for now. Importantly, you have to think of it as we are using commercially off-the-shelf existing, nicely executed algorithms, and we have modified them for usage in our use case. So after applying our algorithms, we will end up getting this graph, which is the actual graph. This is not a simulated graph. This is the graph of this individual sleeping, and we are trying to monitor the displacement level using the thermal imagery based on the optical flow algorithm that we discussed. Now, once we have this, we want to now firstly also filter out all the activity periods. So whenever someone is waking up in the middle of the night, we don't want to be using those time periods. We only want to be using the time period when the person was sleeping and then they had some breathing abnormality. So for that, we again use some simple signal processing, which is basically doing some frame differencing. And if the frame differencing is significantly high in the magnitude, which means if I was sleeping like this and if I've suddenly woken up, I've suddenly shifted my position a lot, so the pixels have changed, the frame difference absolute value has changed. So I would call that as an activity. So I filter out the activities, and after that, whatever is left is what I will use for my further algorithms. Any questions at this point? Okay. So now it comes to the important medical definition of what are the different kinds of apnea events and how do we detect them using the signals we have got. So thus far we're getting two kinds of signals. One is some nostril pixel intensity, which we are getting through the ROI created using the around the nostril. The second is the intensity around your thorax chest, the displacement level. So we have obtained two such signals, which will be in a noisy way looking like this. Now we look at different kinds of apnea events. In this one, can you observe that the respiration from the nostril has stopped? The respiration from the chest has also stopped. So this particular kind of an event is known as the central apnea event. Anyone has a guess on why it's called a central apnea? Where do you hear the term central when you discuss about the human biology? Central nervous system, CNS. So this is an issue with the central nervous system where your brain does not send the appropriate signals for you to breathe. Right? So therefore, whatever we're taking for granted that we're breathing, it's actually a perfect synchronization between the brain, your respiration, organs, etc. So in this case, the central nervous system is not able to send the appropriate signals. So those particular muscles are not activated. As a consequence, you are not able to breathe. Importantly for central apnea, both the waveforms, they become flat. Now, the most common kind of an apnea is known as obstructive apnea. In this case, you can observe that the nasal airflow has dropped significantly, whereas the thoracic abdominal movement is still there, although slightly reduced. So this happens when we saw that particular situation, when your tongue has fallen behind or there is an obstruction in your neck, in the windpipe. Because of that, your chest is still trying to pump out air, but your nostril is unable to because there is an obstruction here. So therefore, in the nostril signal, you will see this reduction in magnitude, whereas in this particular thorax chest displacement, you will not see that much difference. So we are looking at the specific kind of definitions, and you can also observe that sometimes you don't need very complicated machine learning. If you get the signals of a very high quality, you could just use these definitions through the classification. It depends on what kind of a signal you end up getting. And then there is the third kind of event called hypopnea, which is you can think of it as a smaller version or an early version of an apnea. You can think of something like that. In this case, both your nasal airflow and your thoracic airflow movement have been reduced, but by a small amount, 30% or so. And then this is an activity period being shown. So therefore, we are looking at four different kinds of events. Central apnea, both the breathing stop. Obstructive apnea, the nostril breathing is significantly reduced. Hypopnea, both of the breathing is reduced, but by a small margin, and activity is when you have a lot of movement. So again, for this purpose, for validating this, we did a deployment at AIIMS Delhi with about, and at IIT Gandhinagar with about 44 participants, of which 24 had sleep apnea, were diagnosed with, and we had about 21 female participants. We have a very wide range of participants going from 18 to 76. and the total number of apnea events in our data set is about 3,800. So we ended up recording about 7.5 hours of sleep every day for a participant. So about 44 participants, 7.5 hours of sleep. This is the setup at AIMS. So this is the polysomnography kit being put by the AIMS technicians and doctors. In parallel, we are connecting our device and collecting the data. So if there was a question in the beginning, do you collect the data across the two systems in serial or in parallel? In the previous case, we were doing it in serial. In this case, we're doing it in parallel. So both the ground truth system and our system, they're measuring the same quantity of interest in parallel. So this kind of a study design is important to understand. When can we do parallel? When can we do serial? And yes. Mhm, mhm. Yeah. 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 So it's a very interesting question. So his question is that, can you see this nasal probe, this blue plastic-like region? So his argument is that if this particular setup is being used, then you already have something at the nostrils. Whereas in the free sleeping conditions which we had showed, we are not putting anything at the nostrils, which is indeed correct. In the ideal case, our system will work with or without the nasal probe. But unfortunately, because we had to do it in parallel, we had to do away with that. But importantly, actually, this particular setup that we are using, in most of the cases, actually only reduces our signal quality. If that did not exist, the signal quality will only be better. So this is an important point. We have to consider what is the other alternative study design. The other alternative study design is to collect the data from the ground truth system on day 1 and our system on day 2, but the apnea events may not be the same. You cannot then accurately measure. So that's a limitation, but what we are claiming is that our system is working with the nasal probe. We think it will only work better without the nasal probe. So when we did this classification of the different kinds of events, where we had the AIMS doctors do the annotation. So they gave us time T1 to time T2 is apnea, time T3 to T4 is hypopnea, so on and so forth. So based on that, we are now looking at our system and trying to see how many events are we able to match. And the numbers that we're getting is the precision for us is about 0.71 for apnea and about hypopnea is 0.74. These numbers might not look very good, but importantly, while what we'll see is that the metrics that are truly important is what we're doing very well. We also calculate sensitivity and specificity, which are very typical used in the medical literature. So importantly, we want to be using the metric which the doctors use, which is the apnea hypopnea index, or AHI for short. It's a simple formula: number of apnea events plus the number of hypopnea events divided by the number of hours you sleep. So if you have severe apnea, then the AHI is greater than 30. So imagine 30 apnea events. Each event is typically of a 10-second duration. So in 1 hour, this particular person is having at least 300 seconds or 5 minutes of apnea events. It's a very significant quantity. Sometimes I think in the ground truth, we also observed AHI of about 50, 60, 70, something on that order also. So those people have in an hour about 10-15 minutes apnea events. Whereas about 5 events or so, it's considered normal. So 5 events is about 1 minute of apnea events per hour. That's considered okay. So what we said is that this is what the doctors finally eventually use. Can we give the doctors this number as opposed to this specific event level number? This is more for us as researchers, but for doctors, I think we need to give this particular number. And this is the final table we created for the 20 odd participants from AIMS Delhi, which had apnea. The ground truth, for example, for this individual is 14.6 AHI. Our prediction is 15.2. In terms of classification, you might see that the ground truth was mild, we predicted moderate, but the boundary was 15 units. So it's not that big of a deal. Similarly, 13.8 to 19.2, 93.3 ground truth, and we're predicting 114. So think of the ramifications of this. Someone who is severe is predicted severe, someone who is predicted moderate, and this is also borderline, is predicted either moderate or severe, which is the next category. Anyone who is mild or borderline moderate is predicted either mild or moderate. So we are either accurate or we are over predicting by one class, and that too in the marginal cases. And in some cases where we're making mistakes, it does not really matter beyond a certain number, like 93.3, and this is 114. We also spoke with the doctors. They also concluded that sometimes when they see that the participant definitely has severe apnea and they have identified enough events, they do not label each and every event. So that's an important challenge, that the ground truth is always never going to be perfect in such cases, but we have to deal with what we have. Importantly, the quantity of interest is showing very good performance through an algorithm. So to summarize this work, we are saying that the existing systems, they require a lot of instrumentation, about 50, 60 sensors, which make it incredibly hard for someone to sleep, and they require very controlled conditions. As opposed to this, we are saying that we will create a system which does not require any instrumentation, and we can accurately classify these apnea severity in about 89%, and the other cases in which we do not, we're only off by one class. So I'll finish this part and take questions before we move on to the last part. Okay. 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 So the question, I will just repeat for the audience. Can we detect central apnea just by looking at the diaphragm? I am not sure exactly what the doctors do, but I will also tell the other thing. In the other cases, we definitely need the nostril. Yes.
Question was,
Yes.
like,
Yes.
because that is the case where you can probably detect it without doing all other measurements, right? So
Right.
in fact, that was the intention.
Right.
And one more thing is just curious. I'm not sure whether that's not a real question. But if you are measuring the temperature differences using a central area or intensity in a particular region, whether the volume difference between two nostrils, do you have to correct it for that in some sense or not?
Okay.
Is the question.
Okay, so this is a very interesting question. Do you have to correct for the differences between the two nostrils? As you would know that typically during one particular time, only one nostril is more predominant than the others. That's been observed also. So we are in fact, what we ideally want is the volume, but we don't get the volume. So we in fact just get a proxy, which is the pixel intensity.
But precisely that is the reason, in the sense that now you are deciding the temperature using some number of pixels with some intensity within some region.
Yes.
Now, in that case, for some abnormal conditions like that, your measurements might be slightly off. I'm just
Yes.
again.
I think that's an interesting point. So, from the machine learning perspective, we'll have to perhaps go from just object detection to segmentation and get the individual nostrils and see their radii also. But I think that's an interesting point. Thus far, we have not needed to do this, but I think perhaps in the future. Yes. Yes. I see. Okay. Okay. I see. So the other interesting thing, and that might also interest Prashant a little bit more. So in the other RF community, etc., there are other modalities like Wi-Fi. People are using Wi-Fi, radar, etc., to also measure a respiration rate. So, for instance, if this were a Wi-Fi access point, for instance, or a router, now they will look at the signals bouncing off from my chest, and they can measure that. But all those research areas, papers are mostly only looking at your chest because they look at the displacement. So they'll see the signal being sent to my chest and the reflection back and how much time it takes. They can also use sonar and other techniques. But for the nostril, you need something like what we think we have done. Other questions? Okay, I'll go on to the last part. I know I talked about sleep apnea, and I think people are now getting a little tired. Okay. Yeah, so CO2 we have actually not thought. We are actively thinking of at least looking at the SpO2 because the doctors recommend that. So what we're thinking is to keep the instrumentation level low. But like currently it's a single system, but what we are also thinking is if a smart ring plus this can perhaps still be manageable. If we can get at least the SpO2 through that. CO2, I don't know how we'll get that. Yes, I think it's closer to body temperature only. Okay, I do not know that. If Ayush wants to answer that, or we can take it offline. Yeah. Yes. Right. Okay. 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 I see. Got it. 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 So this also is precluding to the talk he's going to give tomorrow, where he's going to talk about remote sensing. And indeed, I believe now he's also going to talk about hyperspectral imaging. So essentially, currently we're looking at a very specific band, which is FIR, far infrared. But perhaps there could be different bands at which, if you observe something, you will see different response. And potentially through that, you should be able to get much more information that you get. Yes.
So do we have to control the environmental temperature for such imaging? Like, for example, maybe an air-conditioned room or something?
Yeah. So when we submitted this paper, we got this question that have you tested out for all the possible environmental conditions, etc., etc. We try to look at the extremes of the temperature which we can maintain, and someone can sleep during that, which is the temperature which you get in your hostels here. So in that range, our algorithms are working fine. So that is what we are hoping to show, that they may or may not, they may break in certain conditions, but the quantity of interest and the signal acquisition, basically what we saw in the morning slides also, the SNR is what we want to see. I think the SNR was more or less stable. That is what we observed. The other thing is that I think even if there is a very large, very cold or very hot, but the delta is what we're looking at in the nostril, and we'll still be able to see something. Other questions? Okay, which brings me to the final part of my talk, which is on a system called SpiroMask. I have about 20 minutes, so I'll go a little quicker. Another interesting thing you can also see here is that most of this is my PhD students' work. So we often think of research as being very linear. First, I'll do this, then I'll do this, then I'll do this, etc. The work I'm presenting is in a haphazard order, in which, not in the same order in which it was done. So oftentimes we don't see this. This is just to bring you perspective. Sometimes as a student, we do not know this and we worry about it a lot. But we think that it's only a linear path to the goal that we get. So now I'm going to talk about lung health diagnosis. We've already talked about respiratory diseases, etc. We will be looking at the measurement of lung health. Again, the same paradigm. We first look at the gold truth, the gold standard. If you want to get a lung test done, it is known as the pulmonary function test. Did any of you were advised to buy any cheap machine from Amazon during COVID? 300, 400 rupees, where you have, so it's an exercise that you could have been recommended. It's a simple machine which has small spheric spheres, and you have to blow out air. You practice so that you are able to move the spheres the maximum distance. So that particular machine is a very simple variant of what is known as a spirometer, where you're trying to measure how much capacity your lungs have. So this is the machine. You clip your nose, you inhale as much as you can, and then you exhale as hard as possible, and then the data gets recorded in this machine, and then you will get some parameters. So typically when you breathe, you're trying to get the estimates of a lung health. You want 2 or 3 parameters. The first is the total volume which is present in your lungs. So you breathe in, then you breathe out as much as long as possible, and when you stop, you look at the, so you get this flow versus time, and when you integrate that, you get the volume. So you get this flow volume curve, the maximum volume, the integration of the flow over time gives you the maximum volume, the lung capacity. There is another parameter known as peak expiratory flow. So your flow will show some pattern like this. You can also try this at your own time. If you try to breathe out, there will be a maxima, and after that your breathing rate will only reduce, your expulsion rate will only reduce. There is another parameter called FEV1, which is the flow at volume equal to 1 liter, or it's the flow at 1 second, I don't recall, one of those. So there is some prior work in this field. What we're saying is that this was during the COVID time, everyone was wearing masks. Can we leverage existing, can we use mask as a variable? People have already done similar work using smartphones for spirometry. What we said is, can we use a mask to measure a lung health through something equivalent of this machine? So what we'll say is that we'll put a very small proxy sensor, in this case an audio sensor. Again, same paradigm. You get the flow rate via the gold standard. Instead of that, now you're putting a audio sensor, which is also in some sense measuring the pressure or the flow. Once you get that audio signal, you can do some signal processing machine learning to learn these parameters, which were FVC, FEV, PF, etc. So this is the setup inside the mask. This is not the prettiest of the setup, but this is only a prototype that we ended up building, a small Nano 33 BLE sense with some audio sensors and N95 and the cloth mask over which we put this and collected some data. So once we perform the spirometry maneuver, which is breathe in as much as possible and then breathe out as forcefully as possible and then as long as possible, we will get this kind of a curve, which is amplitude versus time. You can then do a bit of signal processing, like something known as a Hilbert envelope. Think of this as an overlap. So it's the smoothened out version of the following the envelope of the signal. And then you again do a bit of signal processing, the details of which perhaps are not too important at this stage. Once you get these time series signals, you can extract out different coefficients, which are very common in speech, also MFCC, etc. And once you have done that, you can get these different parameters. So you'll start with, let's say, your raw audio. So you'll get these different features: MEL, frequency, septal coefficient, MEL, frequency, energy, etc. You will then extract these features and then give it to a standard classifier, regressor, whose output is the true values for an individual with FVC, FE1 and PF. We use this mask for two kind of experiments or two kinds of work. One is forced breathing, which is a spirometry maneuver. Second, we can also measure your continuous respiration. So as you're moving around, as you're coming to any particular security entrance, we can also check your respiration rate there, instead of having to put a temperature scanner, which may be showing some lag in showing your temperature and showing if you have fever or not. So that was the aim. We did this study with about 37 participants, 14 of which had some lung ailments, 13 were females, and the age were from 20 to 32. And importantly, so for the first work, we had the gold standard and the respective guidelines. The second one, we had the American Association for Sleep Medicine guidelines. For this one, we're looking at the guidelines from American Thoracic Society, which say that the results of a spirometry machine are acceptable if they are within 7% of the gold standard. So in the first work, when we did the study, we did it serially. In the second one, we did it parallelly. In this case, we are again doing it serially. You cannot blow air into your mask as well as that spirometry machine at the same time. So therefore, what you do is you first you first do the spirometry maneuver on the ground truth machine with this machine. Then you take about a minute or so of rest, and then you perform a spirometry maneuver using this system, our system. And then you look at the errors in these quantities, PF, FEV1 and FVC between the two. Importantly, we observed that the errors are below the 7% acceptable error limit as defined by the American Thoracic Society. And it works both for healthy as well as unhealthy participants. That's the kind of sensitivity analysis we have to do for every research paper. And we also looked at various other things. So when we're looking at measuring the respiration, we also want to ensure that we can measure a respiration in the continuous case at low sampling rates. You don't want, so if the audio is sampled at a very high rate, you'll also get what the people are speaking. So you don't want that. The second is that the error also does not significantly change with respect to the sampling rate. So to summarize, we'd say that SpiroMask will sense both your breathing, your forced breathing as well as the normal breathing, and it worked with both kinds of masks. So overall, I would say that we are looking at, so when I've spoken about these three pieces of work, we're looking at a few future work. One, we're looking at improving the models. So, from the model perspective, currently you have seen we have mainly used, let's say, state-of-the-art object detection methods. Going forward, we are also looking at foundational models. So, they are on the lines of vision language models, etc. What we've also observed from an initial benchmark study is that the vision language models do not perform well on thermal imagery. They perform well on RGB or reasonably well on RGB. They do not perform well. We are also planning to scale these studies to the community level, which is currently we have done studies up to 50, 100 participants, but we want to take them to 2,000, 5,000 number of participants so that it becomes a much bigger diagnosis and similar kind of a setup. And we're also looking to scale these sensing devices as opposed to make them smaller, make the battery longer. So those would be the general rules of thumb which we have to follow for scaling any such device. So with that, I'll end this talk. I will now be open for more questions across all the three topics.